Okay, so what I want to do today to give some baby introduction to Harishchandra's Planchel formula, give some motivation, explain the statement of the theorem, and explain some rough ideas related to the proof of the theorem.
Who's the baby?
What do you mean?
You said baby introduction. Who's the baby?
Yes. Okay, so let's start with our favorite model. So let's assume that G is finite. Then remember I can, what we discussed, what Peter said, that basically if I look at irreducible representations of G and I can look at their characters, so these are functions on G which are conjugated, constant on conjugacy classes, so chi pi of, say, G, T, G inverse is chi pi T. I proved that if I look on G at the inner product, which I think I denoted by integral of G, f of G, say, let's see, f of x, G of G bar, the x, which was just the sum, normalized sum, G. Then these characters are orthogonal to each other. So they form an orthonormal basis of the space of all functions constant and conjugacy classes. So therefore, in particular, I can take the function delta 1, G, complex numbers, which has the property that delta 1 at identity is equal to cardinality of the group G, and delta 1 at any other element is equal to 0, so that I mean it's integral. I mean is 1 with respect to this thing. If I take this delta, I can expand it in this orthonormal basis, and I get the formula. The delta 1 is, so what I will have the sum over all pi's in G hat. Then the coefficient will be the inner product of delta I with a corresponding character. But if I integrate this, what do I get? I get just the value of the character at the identity, but this is the dimension of the representation. So I get that this is dim pi times character of pi. And I can also, if you want, you can interpret this in the following way. You can use the observation that, say, if I look at L2 of G, is the sum of, say, pi, V pi star tensor with V pi, sum over pi's G hat. And I can look at, say, right regular representation. So G acts only on the second factor. The dimension of this space is dimension of pi, and I can calculate the trace, say, of R of x. And because x on the functions on a finite group acts just by permutations, I will get that my character is 0 on all the elements except the identity element, where I just get the cardinality of the group, the dimension of the space of regular representation. So this is, if you want, just the equality of characters. And now I want to fiddle around with this. So let me take arbitrary function on the group, and let's calculate inner product of this function. I mean, actually, I want to multiply f with delta 1 and integrate. And what do I get when I integrate this? So I get f at 1, because, so this is integral over g f of x delta 1 of x dx. I'm nervous with this because these things depend on normalization. Planchel formula depends on the normalization of measures, so I am always worried that I'll mess up something. But this is the sum 1 over cardinality of g, sum f of x delta 1 of x. Delta 1 is 0 for all x is different from 1, so I get the only contribution I get is at the identity, and this is f of 1 times cardinality. This cancels out, so I get this formula. And then, of course, the other side is simple, so this is pi g hat, and I have dimension of pi, and then what do I have here? I have character, the integral of the character times f. So let me just write. No. But we can interpret this. So this is the trace of pi of x. So this is nothing else than the sum pi goes over g hat, dimension of pi times the trace of pi of f. See, I'm trying to formulate my statements in a very similar way as Peter did in his lectures. So this trace of pi is nothing else, in the case of finite group, then I think he did denote it by capital theta of pi. There was some d, but because this is finite sets, we don't care about distributions, and so I will drop this. But this is what we get, that f at the identity is expressed using characters. And now I will replace f by a function on the group algebra C of g. There is this involution which has a nice, which is just makes this an algebra with involution. So I define f of star of g as the function which is equal to f at g inverse complex conjugate. And I mean, this plays some role, especially in the theory, if you're dealing with unitary representations. But here, this is just a minor point. If I replace in this formula f with f tensor convolution with f star, so what do I get? F convolution with f star at identity. This is equal, because of this formula and formula for convolution, you see immediately this is integral over g of absolute value f of g squared dg. So I'm taking the absolute value a square of absolute value over my function and summing over all group elements and divided by the cardinality of the group. And on the other side, I have the sum pi goes over g hat, dimension of pi, and then I have trace of pi. See, this here is replaced by pi of f star f star. And now convolution goes into product, and this star is set up in such a way, I mean, this is something you can easily check, that pi of f star, if pi is unitary, is pi of f star. So this expression here can be written as the trace of pi f times pi f star. And if you ever took, say, some functional analysis, this is sometimes called, this is so-called square of Hilbert-Schmidt norm. But this is just a notation, and this makes perfect sense on Hilbert spaces. So what do we get? We get some formula like this, that if I take function f and calculate its L2 norm, it is equal to dimension of pi times the square of Hilbert-Schmidt norm of pi f over, and you sum this expression over all irreducible representations of G. So this is what works for finite dimensional representations, and with little bit of work you can extend this. I mean, I even want to go into this, but this, I wrote this in such a form that this formally transfers with a little bit of work to G is to compact group. So I can assume here that G is a compact group. Okay, any questions about this? So this is purely elementary manipulation with the notions we already had. And now there are several ways you can view at this. For example, let me start with the remark that if G is a unit circle, S1, what do we get? We get a function on the circle. So this is, say, the integral over G f of G absolute value square d G. This is normalized integral on circle. These representations are parameterized by n, and so pi n of f, pi n of theta is e to the I n, pi n of phi is e to the I n of phi, and pi n of f is just the integral of the representation with respect to f. So this is just n Fourier coefficient of the function f. So if I plug this in here, I get that this is the sum of squares over n's of absolute values of, say, a n square, where these are Fourier coefficients. Of f. So we get Planchel theorem for Fourier series. So this tells us why this is called Planchel theorem. And how you, of course, when we look at the situation, commutative situation, then everything is nice because we start with a group and our Fourier transform is also defined on a group, additive group of integers in this case. And you can generalize this to arbitrary locally compact abelian groups as if you want, and you get the notion of, you get Pontryagin duality and corresponding Plancherel theorem. Here, our G, we are interested in the cases when G is non-commutative. So what we see that here we have group G, and here on the side of Fourier transform, because we can view this side like Fourier transform, we have something more complicated because we are dealing with this dual object, which is just the set of equivalence classes of irreducible unitary representations. But we should think of this side in the following way, that on this side I have a function which attaches to a representation pi in G hat, this pi of f, which is an operator-valued function on the space, say, v pi on which this representation acts. So our Fourier transform consists of operator-valued functions, and then in each space we take this Hilbert-Schmidt norm and we sum with certain weights, and these weights here are given by a dimension of representation. Okay, so this is the compact situation, and now you know that if you look at the real line, you get Plancherel formula, which has, again, some symmetry, but because real line is a commutative group, so you will have integration of real line, and on the other side, you will have Fourier transform also on the real line, and you will integrate again, and there will be just some difference of normalizations of the measures on these two copies of real line, which will appear as a factor in your formula, depending on the definition of this. So let me now give you the formula, just so that you get a feeling for it in the case of SL2, and then I will discuss various aspects related to this formula. Let me point out that there are several ways to view this formula. For example, we deduce this formulas which expresses the L2 norm of the function in terms of the Hilbert-Schmidt norms in representations. This is one way to formulate this. You can look at this formula here, which expresses the value of the function at identity as the sum with some coefficients of the traces of the function in the representation. So you can view this as the evaluating this delta on f, evaluating at the identity, and this is you can view it in general. If G is, say, a Lie group, this will be a distribution, and which is central, constant, and conjugacy classes. These objects here will be characters, so there will be also central distributions in the terminology Peter was using, but also because they're reducible, there will be eigendistributions. So this formula here can be interpreted as an expansion of a particular distribution in terms of invariant central central eigendistributions. But So there are several aspects how you can view these generalizations of Plancherel formula, and I will give you now the expression for SL2, and I will write this formula, and then I'll make comments about this type. So let's assume that our F, if the group is non-compact, I mean, of course, here I should be careful. This F has to satisfy some assumptions, so I think it will. It has to be this has to make sense. So, for example, continuous definitely will be enough for our purposes. On the SL2, because I will be dealing with characters, and we just heard from Peter that characters are distributions, I will assume that our function is smooth and with compact support at the first moment. So let's assume that f in C naught infinity of g, and the formula is 2 pi f of 1. So this, I will make a comment about this 2 pi in a moment, is 1/2, and then I have integral from 0 to infinity. Theta, I have to explain to you what these gadgets are. Theta plus I ni of f times ni hyperbolic tangent pi ni over 2 d ni plus 1/2 integral from 0 to infinity theta minus I ni of f ni hyperbolic cotangent pi ni over 2 d ni plus the sum n goes over z star, so all integers except 0, absolute value of n theta n of f. So let me explain what the ingredients are. So remember, we have our principal series, which correspond to 2 sheets, which appeared in Peter's and Bill's lectures. There was, and I don't know, my notation, the plus corresponds to the trivial representation of m, and minus to the sign representation of m. And then remember, we have these remark which we had that for imaginary on imaginary axis, these representations are unitary by construction, and my ni is of course real here, so I ni is just a parameter of a unitary principal series on the imaginary axis in these 2 sheets. So this one corresponds to this representation. This one corresponds to the representation on the other sheet. What Peter explained to us 1 hour ago is that these characters are distributions. So this makes perfect sense. If he wrote down the formulas, then you would see that the action of this distribution on some function is definitely continuous in the parameter ni. So this is a continuous function. I mean, this, of course, is continuous. And so this integral makes sense. This is the integral which corresponds to the other sheet, unitary representation. So on the other sheet, and these representations are parameterized by n, are the representations of discrete series. And now, Peter, did you label them in the same way, or you have pluses and minuses, your dn's?
This is the character of D, sine of n, sum of n.
Yeah, so theta n is the character. So so you have sine up. And n here. Okay, absolute value of n here. So remember, our discrete series look at there are these limits of discrete series, two of them which correspond in this case to parameter 0. They do not appear in Planchel formula because this guy is 0 in this case. Yes?
Is there any reason why the complementary series doesn't appear?
Yes. We are going to discuss this. Yes. Yeah. Yeah. So, I mean, it's related.
Everybody has his own different answer.
Yes. Yeah, no, I mean, this is, the answer is definitely not obvious, and the answer is so this is the beginning of the story. I mean, Harishchandra, the first proof is a bunch of analytic tricks which show that one side is equal to the other side. And then you know that basically you can argue that this expression has to be unique. And but the argument I want to describe today, and probably I'm not sure that I will manage to say too much today, is basically answers your question. And okay, so again, you can think of this. You can think of this as an expansion of delta distribution at identity, which evaluated on this function f gives the identity in terms of these central eigendistributions on the group, which are just the characters of these representations. Yeah.
What do you mean by central?
I mean, how did you call them invariant?
Invariant is conjugation invariant.
Yes.
And then the other condition is
Yes, okay, Peter called, this is my fault. Peter called them invariant eigendistributions. Some authors call them, in analogy with central function, call them also central eigendistributions. So, okay, these functions here, which appear in the formula, so this is so-called Planchel measure. This is mu plus ni. This is Planchel measure, the piece mu mu minus ni. Let me point out, and I will say a little bit more about this, that these are discrete series, and one of the reasons why they're called discrete series is obvious from the formula, because they enter discretely, Planchel formula. This number, before I erase here, you see here I have, in a compact case, I have dimension of my representation. So this number n divided by 2, absolute value of n divided by 2 pi is called usually formal dimension. So this shows that my choice of measures is not really good one because, I mean, this formal dimension, if you want to be pure, should be an integer. But, I mean, because in my notes I took this convention, this is what comes out. So let me point out, when I mentioned this, the issue of normalization of measures, in a case of compact group, of course, it is critical that, I mean, there is one Haar measure which is kind of natural, and this is a measure such that group has measure 1. For SL2, you don't have any canonical choice, and changing measure on the group, because I can write this Planchel formula in this form, and I should do it actually to make it clear. If I change the measure here, Haar measure, I multiply it by a positive constant, then something will change also on the other side. So I have to do proper normalization of measures to get the right formula. So let me just write down the other formula. So I write this as a 1/2. Oh, no, let me write it 0 infinity. So I'll take pi plus I ni of f square of absolute value Hilbert-Schmidt mu plus ni dni plus this similar term involving minuses So this is the other form or the formula which is equivalent to this. And excuse me? Mu is just the Planchel measure. Or these guys here. I don't want to write these hyperbolic functions. Excuse me? Yes, yes. I mean, this is for one sheet, and this is for the other sheet. So to make sense of the formula, I have to tell you how my Haar measure is fixed. And if you remember, Castleman wrote this formula for Haar measure expressed in Iwasawa coordinates, and so the measure was that f of g dg is the integral of f k a n alpha a dk dA dn, something like that, when alpha is the positive root. So here I have to say what these measures are, and I'm taking A and N, I am representing as R, and I have a Lebesgue measure on R, and I am normalizing this measure on K to be the measure of circle to be equal to 1. So with this normalization, I get this formula.
What's the measure on A?
I identify A, okay, let me just, I identify A with real line, and you are right, I should say what the identification is. Let me just, yes, I am using this This is a very good question. Because I just remember Martina's question from the break, and so my notation is not consistent here. So f a dA is f of t0, 0, t inverse dt divided by t. I think this is the, yes, from 0 to infinite. So this is the A measure, and of course, measure on n. Let me write this for completeness. Is this. So now all Haar measures are fixed, and I mean this formula makes sense.
Maybe you could minimize the fact that
alpha of A, this is the positive root, so alpha of t0, t inverse 0 is is t squared, I think. Let me just double check, but yeah. Yes?
Could you make a canonical choice of Haar measure by choosing an orthonormal basis for K and for P with respect to the Killing form, and then taking the wedge product? Like for K, there is a positive orthonormal.
Sure. I mean, you can do it in a lot of different ways, and I think this is maybe Harishchandra does it this way, but I mean it just changes the formula for a factor, and I mean I definitely, when I was writing up these notes, I didn't have any preference. I just picked one, and you have to stick with one all the time, otherwise your formulas will come wrong. Yeah, but I. Mm-hmm.
And that's dy over dy, but y is a squared, so it's 2 dA over.
Oh, I see. Yeah, but I want to point out to some important things about this before I start discussing Harishchandra's Harishchandra's proof of this in general, which answers all these questions about why there are no complementary series and so on. Because we could view the whole issue as, in our finite group case, we could look at L2 of G and look at its, say, right regular representation on this, and we could try to decompose this. And of course, this is unitary representation, and for unitary representations for nice groups, and our semi-simple groups, in particular SL2, are nice, you can write your representation R always as so-called direct integrals of representations over the unitary dual. And sometimes this mu is also called Plancherel measure in this case. So let me make a few comments about this, because I mean it's important to realize that Plancherel formula carries much more information than this. So what is this direct integral? First of all, this G hat is our unitary dual, so it looks something like this, and a bunch of points. Over the points, I'm sorry, this should be pi. This direct integral is just Hilbert space sum of representations which live over these points, but you can have a bunch of copies of the same representation. If you have a family of representations like this unitary principal series or complementary principal series. They are defined on infinite dimensional Hilbert spaces. So direct integral is basically just the functions on some space with measure, which are with values in the Hilbert space, and then you take L2 of those functions. So you just take measurable, I mean, there are some technical details, but essentially you take the values, functions, the value in, say, this space here, for example, this line, which take values in some fixed Hilbert space on which our representations act by this parameter. So we have minus I nu, and we just have the functions which are square integrable with respect to our measure mu. So this is essentially the idea of direct integral. There are some technical complications if these fibers vary in dimension, but in this case, all the fibers are infinite dimensional, so there is no problem. Important thing to remark is that this definition I just described depends only on the class of this measure. If I multiply the measure with some positive function, I can take the square root of this and stretch out my vectors by that number, and I will get the same Hilbert space. So this decomposition, I mean, this is just, if you heard something about this, it's good to think about this, but it doesn't play too much role in this, that basically this decomposition of the representation determines this mu up to the class. And Planchel formula gives you a specific representative of this class, which also, I mean, it gives you, no, what I'm saying is a little bit too far-fetched, but basically the support of the Planchel measure is also support of this thing over there, but I mean the relationship is different that in the case of compact groups, and you can see that there is a difference because here discrete series enter with formal dimension, and you will see that the multiplicity of discrete series in this decomposition is infinite. So the connection of this decomposition of a unitary regular representation and a Planchel formula is slightly more subtle than in the case of compact groups. But in a way, you can expect from general theory that there will be, I mean, there is an abstract Planchel theorem, if you want, which gives a Planchel measure on this. And as you remarked, from general theory, in principle, Planchel measure could live on a complementary series. But this is not true, actually. And let me use last 15 minutes to give you one way of looking at this which is relevant for our other applications. I don't think you will be too thrilled about this because we need more distributions and more funny spaces of functions, but this is fact of life. So let's look at a particular matrix coefficient, which, I mean, Kasselman alluded to this in one of previous lectures. So I'm taking this principal series representation for a parameter n equals 0. And I'm taking, it contains trivial k-type. So a k-type which transforms under representation tau 0 of k. So let me denote this unit vector there is 0, and I can look at pi of x is 0, is 0. So this is diagonal matrix coefficient there. Harishchandra called this Xi function, capital Xi function of X. It has some remarkable properties. And for example, this function is always positive. And the reason why it's always positive, I mean, this is a diagonal element of a matrix, and so if you unitary matrix, you apply complex conjugate, you get the matrix of X inverse, but X inverse and X are conjugate by an element of K, by this element W, which appear in lectures. So from this you can see that this is real, and then you can even write down a formula, and you see that this is actually positive. So this is the first remark. The second remark is, if you look at the expansion, I mean, remember the leading exponents of these representations look like 1/2, 1 plus, let's see, in my parameterization, I should put I in E. Is this, Peter, is this consistent with your notation? Yeah. So of course, here I in E is 0, so I take this thing out. So basically, if I look at the behavior of my Xi function as I approach 0 in asymptotic expansion, this function Xi of A behaves as alpha A to 1/2. So it decays towards the origin. This is one remark. The other remark is that other matrix coefficients of this unitary principal series in both axes, they have leading exponents that look like this, and of course alpha A to I nu is just an oscillatory term. So the behavior, roughly speaking, all matrix coefficients when they approach 0 have the same qualitative behavior as Xi of A. And then Harishchandra introduced also one function which is, so you look at the Cartan decomposition KAK, you write an element of A as e to the t 0, 0, e to the minus t. Harishchandra liked Lie algebra coordinates, so this is an element in A. And I can define a function which on such element takes the value, I need to do it only on this A plus, takes the value, absolute value, okay, in this case my t is positive, takes the value t. And then I conjugate with k and I get a k bi-invariant function on the group. So sigma of k1 a k2 is equal sigma of a. And this sigma of a is given by sigma t 0, 0, t, let's see, e to the t is equal to t for t in A plus, which is this piece over here. I mean, I am taking, if you want whole A, then I would put absolute value. See, let's see, you are right. I am taking this, my t is negative. Yes, thanks. Yes. I just, so I have two functions which measure growth of my functions on the group. One is this Xi function, which behaves in a Lie algebra coordinate exponentially, because you see what is alpha A of this matrix is the square of this entry, so it's e to the t, and then I'm taking square root, e to the t square, and then I'm taking square root. So this function behaves like e to the t when t is negative, and this function sigma behaves like absolute value of t. So this is what Harishchandra needed to measure the growth of the functions at infinity. Then he defined so-called Harishchandra-Schwarz space, C of G, in the following way. And I mean, this will give you some idea why. So this is a space of smooth functions on the group. So these are f from G into C, which are smooth, and have the following property, that if I look at any invariant differential operator, D1 and D2, so this one is, say, left invariant on G, and this one is right invariant, then you require that absolute value of D1, D2, f of x times C of x inverse times 1 plus sigma of x to some power r is bounded, so the soup of this exists. For any left and right invariant differential operators, and then is, yes, it's bound. So this is, this function is bounded for any r, of course we care just for positive r's, and for any left and right invariant differential operators. And this gives a family of seminorms, and this family of seminorms defines a locally convex topology on this. So this is called Harishchandra Schwarz space.
R is any real number, or just
R is, I mean, I think Harishchandra uses a real number, but you could take an integer, positive integer. I mean, it's, you just want to have something which grows at infinity, or polynomially in a Lie algebra coordinates. I think this is. Yes, I mean, and Xi gives you a fixed exponential term, and then you allow either all logs or all powers of t, and you control this. This topology is essentially uniform convergence of expressions of this form. Apply differential operators d1 and d2 for any d1 and d2 left and right invariant, and multiply this with this function which grows at infinity, and ask that the product, that these products converge uniformly. Or you can just define P d1 if you had some locally convex spaces course, you can define seminorms as these supreme, and then this defines local the convex topology and C of G. So this is a space of functions which decay with certain exponential rate of decay at infinity. Yeah?
What is this function sigma? I mean, you have just defined it like this, or it has some other significance?
Yeah, I just define it like this. You want to have something which goes in Lie algebra coordinates polynomially. I don't think there is any much deeper sense in this. So this space, so you see, this morning we had this discussion, what about distributions? Can't we look at some space which are not compactly supported? And you see the problem here, if you have smooth functions on full G, then you have to use invariant differential operators to define this uniform convergence of functions in all your derivatives, because otherwise you could take differential operators which grow like crazy on the group, and then of course this would put very much stronger condition on F's. So if you have functions with non-compact support, then you pay for these conditions by having to use these invariant differential operators. But I mean, these are just technical details you shouldn't worry too much about. Oh, my. What? Here, yes. But when you define spaces of distributions, what Peter was doing this morning, you don't have to do it because you are on a compact set. Okay, so then using all these tricks, I mean, this is quite a lot of work, but it's nothing very deep. What do you see? First of all, you see that this Schwartz space consists of functions which, I mean, it's a C of G with this topology is complete. So this is the first thing, and it's also Frechet space, but you don't care too much about this. Then second property is that C of G is a convolution algebra. So basically, we define convolution of functions with compact support. Because of these growth conditions, you can see that convolution is well defined for two functions from Schwartz space. Then the third property, which is important, is that matrix coefficients of discrete series are in the Schwartz space. This is rather easy. If you look at Peter's formulas, then for leading exponents, you see that the matrix coefficients of discrete series decay faster than a Xi function. Because, I mean, Xi function has an exponent of this type. For a discrete series, you have exponents which are integers. So matrix coefficients decay faster than the Xi function. If you take a matrix coefficient and apply one invariant differential operator, right or left, this is like applying on the corresponding vector the corresponding element of the enveloping algebra, so we get another matrix coefficient of discrete series. So basically there is no problem with this. This Xi function, I mean, cancels out the growth of this, and you get something which decays, and therefore definitely this stays bounded on the group. And you can look at the closure. So let me denote by C naught of G is the closure of the space spanned by matrix coefficients of all discrete series So this is what Harishchandra calls space of cusp forms. And you can define this, and one can easily show that this space is a two-sided ideal in this algebra. Okay, so I'm already over time. Let me just, I'll take 2 more minutes to give you some indication what's going on after that, and then next time we are going to continue. When you have this Harishchandra-Schwarz space, then continuous linear forms on Harishchandra-Schwarz space are called tempered distributions in sense of Harishchandra. I mean, one can show that all of these characters of these representations extend to tempered distributions. One property I forgot to mention, that smooth, compactly supported functions are, of course, contained in a Schwarz space and dense in it. So if I have a character which is a linear form on this, if it extends to a tempered distribution, it extends uniquely because this is a dense subspace. So all of these characters extend to tempered distributions, and basically Planchel formula holds not only for functions which are smooth with compact support, but for functions from Schwarz space. And the answer to one answer to your question is that none of these representations in complementary series have tempered characters. These representations are not tempered because basically their characters are growing so fast that they cannot be applied to Schwarz functions. Harishchandra-Schwarz functions kind of decay, but they don't have a compact support. So if you try to apply a distribution given by a function which grows fast, then the integral will just diverge. And so therefore, you cannot extend those distributions from this space to this space. So this is one reason why complementary, one of the million ways to see why complementary series shouldn't appear there. Let me just finish that why this Schwarz space is good, because one can write another ideal, so-called ideal of wave packets, and this ideal and the ideal of cusp forms, their product is the Schwarz space. So basically, the proof of Planchel formula reduces to 2 pieces. One is the inversion formula for wave packets. The other one is, say, the Planchel formula for the space of cusp forms. And I mean, this is, you can ask from where these Planchel formulas come and why they look like this, and this is something I hope to address today, but it's always one can do much less than expected, so I'll talk about this next time. Any questions?